Hi everyone, so today we're gonna do selected problems for lab 13 to not consolidate, but expedite the video process. I have my work written out and then I'm going to make check marks with a red pen so that you can see what step I'm talking about. So for problem 1, it just wants us to verify that the values actually are a solution. So this one should be pretty easy for you, but just a reminder in case you've forgotten. To verify, we put in 2 for x and -1 for y, and we put a question mark here because we want to see if it equals it. So we go to this step, then we say, okay, 4 plus 1x, does it equal 5? 5 equals 5, great. We verified it for the equation 1. For the second one, we plug in the same values, but for the second equation. So right here, we're plugging in 2 and -1, simplifying, we get 8 equals 8, it's verified. If we get an answer that says like 4 equals 7, then it's not a solution. But here, since it says verify, that means it is a solution, which means if you get something different than this, then that means you did something incorrectly. So we'll move on to number 2a. So here's what we're given right here. Right from the get-go, we see that x is in the denominator and y is. So we have to say x does not equal 0 and y does not equal 0. Which means if somewhere in the problem we get to a point where we say x equals 0, that's an extraneous solution. So just keep in mind your domain and range. So here's a little note I made, which is 3 over x is the same as 3 times 1 over x. So here I solved for 1 over x by subtracting the 1 over y, and then I plugged this value in here. So we have 3 times 8 minus 1 over y minus 5 over y equals 0. Then we just distribute. We get 24 minus 3 over y minus 5 over y equals 0. 24 equals 8 over y. And we get y equals 1/3. So then we can plug it back into the original, to this equation. And say 1 over x equals 8 minus 1 over 1/3. 1 over x equals 8 minus 3. 1 over x equals 5. Here we're multiplying by x, and then we're dividing by 5. So x equals 1/5. However, that is not your full solution. Right here is your full solution, which is a geographical point of 1/5, 1/3, with our x and y values that we found, and neither one of them is 0. So that means we don't have any extraneous solutions for good. So then we'll go to the next problem. Okay, so this says solve each system of equations, and if it doesn't have a solution, say that it's inconsistent. So the first thing I always do right here is I number my equations, because without that it's really easy to get confused, and as a grader I can tell you it's much easier to follow if you number your equations. So now this is 3 equations, 3 unknowns, which means we can't just solve for one variable and plug it into the others like we can with 2 variables. So we have to eliminate. So in this step right here, I am multiplying equation 1 by -3 and leaving equation 2 the same. So I get -3x minus 12y plus 9 equals 24. And I'm adding them together to get this fourth equation. Okay? And notice that I got rid of my x, which is why I did this. So in this step, we want to get rid of the x again so that we don't want to get rid of a different variable is what I'm saying. So we have -1 times the first equation plus 3, just 1 times the third equation. And when we add them up, we get rid of the x, and you have -3y plus 9z equals 9. And I'm calling that equation 5. So here we get to take our 4 and our 5 that we just found, because now we have two equations, two unknowns, and that's much easier to do. So here I did negative 4/3 times equation 5, so that we got our z's to be the same, well, same and opposite. So when we add them together, we get negative 9y equals negative 12, divided by negative 9 on both sides, y equals 4/3. Now that we have the 4/3, we can plug it into either 4 or 5. It doesn't matter which one, but it has to be one of those two. So right here, that's me plugging in the 4/3, so negative 3 times 4/3 plus 9 is equals 9. Negative 4 plus 9 is equals 9. 9 is equals 13 divided by 9 is equals 13/9. And now since I have y and z, I can plug it into either equation 1, 2, or 3, but I just picked equation 1. So I said x plus 4 times 4/3 minus 3 times 13/9 equals negative 8. When we simplify, we get this equation. We simplify, and then we get x plus 1 equals negative 8, x equals negative 9. And again, that's not the full solution. This is the full solution when we put it into a coordinate, a set of coordinates. So negative 3, 4/3, 13/9 is a solution where these three equations intersect in 3D. Go on to number 4. I'm not going to solve it all the way because it's really similar to what we're doing, but this is a basic word problem that you should be able to figure out. If you remember at the beginning of the semester, we emphasized not using two variables. We were like, always make things in terms of one variables. Um, Here we can finally make it with two variables. But this is how I want you to make your variables and define them on an exam and on labs if possible, because this is very, very clear. I don't want to see you say A equals adults or whatever, because then I don't know what about the adults you're measuring. Because there's a cost for adults, there's a number of adults. This really specific definition with A equals the number of adults watching the movie and S equals the number of senior citizens watching the movie is very specific and easy to follow. So the thinking process here, when you read this question, I tend to skip the prices at first. Then I go on a day when 325 people paid for admission. Well, what were those 325 people? We were told that the only options for those people to be are either adults or senior citizens, which means right now we get this equation, that the number of senior citizens plus the number of adults must equal 325. And then we get total receipts here, which means the revenue basically. And revenue is always price times quantity. So in this case, we have price times the quantity of adults plus price times the quantity of seniors, which ends up being 9A plus 7S equals 2,495 because that was given in the problem. And so were the prices. So this is two equations, two unknowns. You guys definitely know how to solve this. You'll solve for S or A and then plug it into this equation. Of course, if you have questions, you can ask on lab, but I think you know how to do this. And the setup is the most important part. So this whole section is what I want you to be able to do. The algebra hopefully will come later, but this is important. We'll move on to number 5. It says write the system of equations corresponding to each augmented matrix. Then perform the indicated row operations on the given augmented matrix. So this first part is just rewriting it. So here we have 1 times x plus negative 3 times y plus 4 times z equals 3, which is what we have right here for the first row. Here we have 3x minus 5y plus 6z equals 6, and here we have negative 5 plus 3 y plus 4z equals 6. This skill of being able to translate between matrix form and equation form is really important. I will make note that you can choose to write xyz, or you can choose to write x1 minus 3x2 plus 4x3 equals 3, and then carry that down. You can pick as long as you keep it consistent. If this is x, then all of these have to be x. If this is x2, then all of them have to be x2. So then we're doing these row operations. This says you take -3 times row 1, add it to row 2, and then replace row 2 with that. So I always write the work like this, and especially on an exam, that's good practice, because if you do it in your head and then I don't see this work and you make a tiny error, I don't know if it's just a sign error or something small, or if you just didn't know how to do the problem. So as far as partial credit goes, you want to show this at some point. So -3 times 1 plus 3 is 0. -3, so actually I'll show you. So -3 times 1 plus 3 is 0. -3 times -3. This is where these numbers are coming from. This 1, this -3, this 4. Um, so -3 times 4 plus 6 equals -6. So this is the new one. So this first row stays the same. The third row stays the same. The only one that changes is this middle row. And then it asks us to do this one, this 5 row 1 plus row 3 replace row 3. And here's my work that I would like to see when I grade your work. So 5 times 1 plus -5 is 0. 5 times -3 plus 3 equals -12. 5 times 4 plus 4 equals 24. And 5 times 3 plus 6 equals 21. And again, the 1, -3, 4, and 3 is coming from this row, and then row 3, the -5, 3, 4, and 6 is coming from this row. And this is all this problem asked us to do. This is just helping you practice, but you'll notice that this is a 1 on top and 2 zeros on bottom, and that is what we strive for when we do this type of thing. So this is actually doing what you're already supposed to be doing. Go to problem 6. Now this is giving you the reduced row echelon form, which is the most reduced a matrix can be. And it's asking you to write the equations and then determine if it's consistent or inconsistent. And if it's consistent, give the solution. So just writing the equations, we have 1x plus 0y plus 2z equals -1. 0x plus 1y minus 4z equals -2. And 0x plus 0y plus 0z equals 0. So what we mean by consistent here is, does this make sense? Okay, if we get an answer that has like 0 equals 2, that would mean it was inconsistent because that doesn't make sense. That's illogical. So often when a matrix has some numbers, and then it has like 0, 0, 0 augmented with like 4, then we'll say it's inconsistent. But this one is consistent because there's no nonsense. So when there's a row of zeros like this, that tells you there's a free variable. But what that really means is you solve for, it means z can be anything. So if we solve for x here, then x, by pulling this 2z over, equals -2z minus 1, and y equals 4z minus 2, and z is just whatever. Z can be anything. So again, this is not your full answer. This is your full answer, where x is -2z minus 1, y is 4z minus 2, and z is just z. Which might seem a little weird, but it's sort of like if you go on Desmos and you make a function with a slider. Um, when you move the slider, you change the function. So it only depends on that one slider, not necessarily all of the other stuff. So that's a little bit like that. So that is the solution for that one. It says solve each system of equations using matrices, which means row operations. If the system has no solution, say that it's inconsistent. So we start by turning this system into a matrix right here, and we want this number to be 0. So what can we multiply by row 1 and add to row 2 to get 0? Well, -1. So negative row 1 plus row 2 replace row 2. And here's what we get. Because -1 plus 1, -1 plus -1, -8 plus 4. So now we want this number to be 1. So you can't divide numbers in matrices, but you can multiply by a constant. So we can have -1/2 times R2 replace R2, which means we end up with this, which is the first row stays the same, second row turns into 0, 1, 2. And then here we want this number to be a 0 for it to be in reduced echelon form. So we have negative row 2 plus row 1 replace row 1. So here we're sort of doing the reverse of what we have been doing. And here's the work for that. And then you get 1, 0, 6, 0, 1, 2. And right here, I'm sure you'll talk about it soon if you haven't already, is the identity matrix. And this is important for a lot of stuff eventually. So here we write an equation. So we have 1x plus 0y equals 6, 0x plus 1y equals 2, which means x equals 6 and y equals 2. And again, that's not the full answer. This is the full answer, which is a point where these two equations intersect. These are the two lines that intersect at one point. Which means, of course, this is consistent because it has an answer. Okay, so this is a 3x3, and they are definitely a little more tricky, but they're still doable. So the first things first is to put these equations into a matrix. And this one already is a 0, so that's good for us. Now we want this 2 to be a 0, so we go -2 times R1 plus R2, replace R2, and we get this matrix right here. And I'm going a little faster so you don't have to watch everything, but you can feel free to pause and look at the work and stuff, which is over here. And then from this matrix, we want this to be a 0. So we do negative row 2 plus row 3 replace row 3. And we get here. And then from here, we could go into reduced row echelon form, but it's more tedious that way. So instead, we're just going to start from the bottom up. So this equation right here translates to this one, which is 0x plus 0y equals 4 plus 4z equals 0, which means z equals 0. So now we can plug it into this second row, which is 2y minus 3 times 0 equals 4, 2y equals 4, y equals 2. And then we can plug it into this first row, which is 1x minus 1 times 2 plus 0 equals 6, which is x minus 2 equals 6, x equals 8. And again, that's not the full question answer. This is the full answer where we put 8 where x is, 2 where y was, and z for 0. So again, this is a point where these three lines intersect in 3D. Okay, so this looks kind of complicated, but it's not awful. It just requires some work. So this question right here is a little weird looking, but it's not awful. So we know that it's going to have this equation. And then it goes through these points. So the first thing I'm going to do is plug in the points. So first we're going to plug in 1, 2 here. That's where we get the 2 and the 1 and the 1. I'll plug in the -2, the -7 to this one. It's -7, -2, -2, and the 2, -3, and for this one. Which means now we have this set of equations. And just to make it easier, because we typically put the constants on the other side, it doesn't really matter, but just so we're familiar, we're putting it to the other side so that we can use a matrix. And I went ahead and put, well, actually they were already in order, but all the A's are in one column, all the B's in another, and all the C's in another. So here is a matrix made from those equations. So 1 is the coefficient here, -2 is the coefficient here, etc. So all of the coefficients and constants on this side are the same. So like always, we want these two numbers to be 0. So we do -4 row 1 plus row 2 replace row 2, and -4 row 1 plus row 3 replace row 3. Now, these happen to be the same numbers, but that's just a coincidence. And I went ahead and showed you that the green corresponds to the green and the blue corresponds to the blue, which gives us this one. So now this is a preference, it's not necessary, but I prefer my smaller magnitude numbers to be on top. So I swapped 2 and 3. Then from here, I can do negative row 2 replace row 2, which is just multiplying it by -1. And for row 3, I'm going to multiply it by 1/3. So that gives me this matrix where row 1 stays the same, row 2 became positive, and row 3 has a -2. You'll notice that now these are the same but opposite numbers. So here I did row 2 plus row 3 replace row 3, which means row 1 and row 2 stay the same, but row 3 turns this into 0. And again, we could go into reduced echelon form, but that would be more tedious in this case. So instead, we're just going to write this equation from right here. This says 0x plus 0y plus 2z equals 6. Or 2c, sorry. 0a plus 0b plus 2c equals 6. So 2c equals 6, c equals 3. So then we plug it into this second row, and we have 2b plus 3 times 3 equals 11, 2b equals 2, b equals 1. And then we can plug it into this first row, so a plus 1 times 1 plus 1 times 3 equals 2, a plus 4 equals 2, a equals -2. And again, that's not the solution, so this right here is the solution of the system of equations we just solved. However, what did the question actually ask for? Always double check that. It says find the function y equals ax squared plus bx plus c, whose graph contains the following 3 points. Which means our actual answer is this one, because we plugged in -2 for a, 1 for for b, and 3 for c. So that function is the one that has all 3 points on it. Okay. Oh. 10. Okay, finding the value of a determinant that's a 2 by 2 determinant. I will mention that these lines, these straight lines, mean determinant, and these brackets mean a matrix. So when I want to say the determinant, so the matrix 6, 4, -1, 3 is a matrix. If we want the determinant of that matrix, we either write it as bar 6, 4, -1, 3, or DET, and then we write the matrix. So the bars and the brackets are not the same. They do mean different things. Okay. But for 2 by 2 determinants, it's super easy. You take this main diagonal starting in the top left corner and multiply. So 6 times 3 is right here. And then you subtract this diagonal, the top right corner. So it's minus and then 4 times -1. Now a lot of students mess up when there are double negatives and stuff, so be extra careful to write it like this so that you can get it correct. So in this case it's 18 minus -4, which is 18 plus 4, which is 22. So pretty easy for that one. Okay, now here's where you find the determinant of a 3 by 3, which is trickier. You should have seen in class, or you're about to see, that there's a pattern with the signs that's up here. So you start in the top left and there's a plus, and then you alternate. So no matter which way you go, up, down, left, right, not diagonal, of course, but up, down, left, right, you will always be alternating signs. So here's where that comes into play. For this determinant, we can go across any column, we can go down any column, or across any row. A lot of the examples show across the top row, but that is not always the easiest one. So we in particular, if there's a 0, we want to use a column or row that includes that 0. So we are going to go down this column. So here, this is a plus from up here. So that's what this +1 is. And then we multiply by this number, which is the 2, and then multiply by the 2 by 2 determinant that occurs when you cross out those two side ones. So this is what's left over. Okay? Then here we have a minus sign from this guy times 0. And really at this point, we don't even care what this determinant is, but I wrote it down so that you're familiar with the pattern. So the pattern is we go to the 0 and we make a line across and down like a T, and we make a determinant from what's left over. So the 4, -1, and the 1, -3. And then here we have a +1 from up here, a 4, because that's what this number is, and then a determinant that's left over when you cross out this column and this row. So this is what's left over. Okay, and then from there it's just some algebra. So we have the 2, and then remember this is a 2 by 2 determinant, so 6 times -3 minus -1 times 1 minus 0, because we don't even care about the determinant. This is why we chose this column, because if there's a 0 in the column, we just got rid of a third of the work we had to do, which is super helpful when we're in a hurry. And then here we have 4 times -1 minus -1 times 6. So 2 times 18 plus 1 plus 4 times -4 plus 6. 2 times -17, 4 times 2, -34 plus 8 equals -26. And then this is your final answer. And there are a couple determinants later on, and I'll make sure to do them in different directions so that you can see that it works no matter which column or row you choose. So I'll move on to number 12. It says solve each system of the equations using Cramer's rule if it is applicable. If it's not applicable, say so and use another method. So I'm going to go over the notation I use. It might be a little different than Mrs. Kinder's, but I'm going to show you this way because this is how I know how to talk about it. So here I wrote down x vector, and you don't have to understand the term vector necessarily, but all I mean is that this is the x column. Here's the y vector, or the y column, which comes from right here, the 1, -1. And the b vector is the constant vector, or the constant column, which is this 8, 4 right here. So that's what I mean by this. So the equations for the x coordinate, which is not the x vector, is dx over d, and y coordinate is dy over d. So d right here is the determinant of the coefficient matrix. So here is literally taking these four numbers and putting them in a determinant. So once you take the determinant, you have 1 times -1 minus 1, and this equals -2. Now since we're dividing by d in both of these cases, the determinant can't equal 0. So -2 does not equal 0, which means Cramer's rule is applicable. If our d value had been 0, we would say Cramer's rule is not applicable, and when the determinant is 0, then either there are no solutions, meaning like the lines are parallel, they never intersect, or there are infinitely many solutions, which means they're the same line. But either way, you can't use Cramer's rule. But we can here because of this -2. Now, dx, that's denoted by taking your D matrix and replacing your x column with your B column. So here we have 8, 4 from over here, and 1, -1 from the original. And we take the determinant, and we get -12. dy is leaving the x column be where it's supposed to be, and replacing the y column with the B column. And then we take the determinant, and we get -4. So the x column is dx over d, which is -12 over -2, which is 6. And the y coordinate is dy over d, which is -4 over -2, which is 2. And again, that's not your final answer. Your final answer is a point. So we'll move on to the next problem. Okay, now this one looks kind of gross. And if you're confused, I recommend pausing and looking at some stuff, but I'm going to explain it verbally also. So it says solve with Cramer's rule if applicable. So I'm showing you how to do the whole problem from start to finish. On a test, you would not be asked to do the problem start to finish. The two options are either you will be given your D determinant, which is given here in this problem, and then you don't have to find that, but you have to find X, Y, and Z. Or you'll be asked to find like only the Z coordinate or only the Y coordinate of the answer. So don't be scared that you're going to have to do everything that I'm showing you. At least one of the things is either going to be given or you won't have to do all of the work. But here I wrote my x vector, which is my x column. Oh wait, no. X column, y, my y column, z, my z column, my b is my constant column. So my d, now this says you don't need to show that d equals -3, but I'm showing you so that you see how to do it. For this one, I went across this row. So it goes plus, minus, plus. That's why there's plus, minus, plus. And then the numbers are 1, 1, and -1. And then determinants are left over when you cross those two out, you get here. And when you cross those two out, you get this one. And when you cross those two out, you get this one. So then we just simplify our work. That's algebra, which we've done a little bit of, and we get -3, which is what they gave us. So if it says you don't have to show it, you don't have to show it. I'm just showing you this so that you can see very clearly that you can go across several. So this one, we went across this row. For my dx, we leave our x. No, we don't leave our x. We change our x to be the b value, but our y and z stay the same. And this green line that I wrote means that I went down the last column. So it's going to be plus minus plus, which is where these numbers come from. -1, 1, -2, which is where these three numbers, and then the determinants that are left over. So the first one would be when you cross out these two. The second one is when you cross out these two. Oh, where's the? And the third one is when you cross out these two. Well, now I. Okay. So this means we can go all the way across. So we got an answer after some simplification. You're free to follow my work. And it equals -3. That is a coincidence. That's the same as the d value. It just happens to be the same because it's nice numbers. For dy over here, I went down the first column, which is plus minus plus, which is where these plus minus plus comes from. 1, 3, 1, which are these three numbers, and then the determinants. So first I cross those two, then I cross those two, then I cross those two, and whatever's left over is left over. Okay. And after some simplification and doing determinants, we get -9. And I'm writing this all here so that I have it all in one spot. Okay, and then dz is when you plug the b vector, the constant vector, in for z, but leave x and y the same. And this time I'm going down the middle one. So in general, you want to pick the direction that's easiest, but I'm picking this one to just show you that it can be done. So since it's here, it's plus, minus, plus, but we're going down. So it's actually minus, plus, minus. So minus, plus, minus are where those came from. Then we have the 1, the -2, and the 3. And then we have the determinants that are left over whenever you make a t. So first it would be these two, then it would be these two, then it would be these two. Okay. And after some simplification, we get to 6. And then we put it into the formula. So x equals dx over d, which is -3 over -3, which is 1. Y equals dy over d, which is -9 over -3, which equals 3. Z equals dz over d, which is 6 over -3, which is -2. And that's not your final answer. The final answer is a point. 1, 3, -2. Okay. So this one says tell whether the given rational expression is proper or improper. And if improper, rewrite it as a sum of a polynomial and a proper rational expression. So for proper, we look at the degree. So because of this 3 right here, the numerator is degree 3, and this 2 means the denominator is degree 2. Since 3 is bigger than 2, it's an improper fraction. And the way we follow the directions is we we use long division. So don't forget your placeholders, and we divide 5x to the third plus 2x minus 1 by x squared minus 4, and x squared times 5x is 5x cubed, so then you multiply by everything again, and you get 5x cubed plus 0x squared minus 20x, and you're subtracting all of it, which means the same as switching all of the signs, which means you're adding, and then you go 0, 0, and then this is 22, and then you pull down the 1. Now you can't fit x squared into 22x, so that's part of the remainder. So this original that we had is now equal to 5x, which is a polynomial, plus a proper rational expression, because this is a degree 1 and this is a degree 2. So it is proper, and this makes sense that our remainder would be a line because we had a cubic over a quadratic, so like x cubed over x squared equals x, so this makes sense. And this is our final answer. The reason this is showing up in this section is for partial fraction decomposition, a rational expression has to be proper. So if a rational expression is not proper, you have to do long division first and then do partial fraction decomposition. So we will go to number 16. So now it's the factor partial fraction decomposition. First things first, check if it's proper. We have degree 1 over degree 2, proper, which means we can use partial fraction decomposition. Our first step should always be to factor the denominator if we can. So this is how we factor the denominator. That's just rewriting the original. And right here, I have little arrows that point that these are linear. So x plus 2, if you graphed that, it would be a line. Or x minus 1, if you graphed that, that would be a line. And it's to degree 1, so it's non-repeated. So it's non-repeated linear. When it's a linear case, you write it like this. So remember, we're doing adding fractions but backwards. So we end up with a, which is a constant, over one of the linear terms, and b, which is a constant, over the other linear term. And then after we set up this whole problem, we can multiply every term in the problem by the denominator of this side. So in this case, it's x plus 2 times x minus 1. When you multiply this by this first term, both of the denominators cancel, so we're left with 3x. When you multiply it by this a term, the x plus 2 cancels, but the x plus 1 remains. And when you multiply it by this b term, the x minus 1 cancels, but the x plus 2 remains. So then we distribute, so 3x equals ax minus a plus bx plus 2b. And here we're grouping it, you're factoring in an x. So we leave the left side alone 100%, but here we take everything with an x in it and we factor out the x out front, and we left with a plus b on the inside. And we have all the constants and put them in their own term. Now, side note, if you see this right here, if ax squared plus bx plus c equals dx squared plus ex plus f for all real numbers, then it's intuitive that a must equal d, b must equal e, and c must equal f. Otherwise, this wouldn't make sense. So that's the property that we're going to use in this case. So we're going to take the coefficient of x and compare them. So here, the coefficient of x is 3, and here the coefficient of x is a plus b. So we have the equation 3 equals a plus b. Then here we have constants. Now over here we don't have a constant, so the coefficient is 0 because it's 0 times a constant. And here this is our constant because it's everything without an x. So we have 0 equals negative a plus 2b. So we can solve a equals 2b. And now we can plug in this a for this a. So 3 equals 2b plus b, 3 equals 3b, b equals 1, a equals 2 times 1, which is 2. Now, this is not your answer. Finding a and b is not your answer. You have to plug it back into the original. So here are where your a's and b's were. So now we're saying that this original rational expression is exactly equal to 2 over x plus 2 plus 1 over x minus 1, because our a went on top of this one and our b went on top of this one. So you have to plug it back into the original up here for your answer to be correct. And you can prove this to yourself. If you want to add those together, you're going to have to find common denominators, and you should end up with this part, because that was the whole point of this. And this comes back in Calc 2, especially in DiffyQ and a couple other places, so it doesn't really go away. For 17, it says find the partial fraction. First, check if it's proper. So the top is degree 2, the bottom is degree 3, 2 is less than 3, it's proper, we can do partial fraction decomposition. So first step, try to factor the denominator. Now, x is already factored out. This part looks kind of funny, and I'm not sure if it factors. So you can check the discriminant, which is 3 squared minus 4 times 1 times 3, which equals 9 minus 12, which equals negative 3. The discriminant is negative. That means this does not factor, which means the type is an irreducible quadratic. So the type for the x is a linear type, because if you graphed it, it would be a line. The type for this one is an irreducible quadratic. It means a quadratic that you cannot factor. So we rewrite the original problem, and then we have a over x, because that's a linear term, so the top needs to be a constant. And here we're having the irreducible quadratic on the bottom, and that means if the bottom is degree 2, then the top is at most degree 1, which is why we have bx plus c. So if it's a quadratic on the bottom, then it's going to be a line on top. So now we multiply every term by the denominator. So when we multiply by the original, the whole denominator cancels. When we multiply by the a term, the a cancels, but the quadratic remains. When we multiply by the b, x plus c term, we get the quadratic cancels, but the x remains. So this part is kind of tedious, I will admit, but it's sort of just how you have to do it. So here is just a bunch of distributing, and I will actually rearrange. I'll put the x squareds together and the x's together and the constants together, and then I'll factor out the x squared, the x, and the constant. And now we're going to compare coefficients. So the coefficient of x squared on the left is 1, and it's a plus b on the right. For x, the coefficient is negative 11, and on the right is 3a plus c. And on the left, the constant coefficient is negative 18, and on the right is 3a. This right here gives us immediately this and says that a equals negative 6, which means if we plug it into this equation, we get c equals 7, and then we plug that one into this first equation, we get b also equals 7, which again is a coincidence that doesn't always happen. So now that's not the answer, we have to plug it back into the original, which means the original thing that we were trying to find the partial fraction decomposition of equals this, because negative 6 over x plus 7x plus 7 over x squared plus 3x plus 3. So it's a little tedious, but it's not impossible. It's just a lot of algebra, and then you have to solve a system, which is why it's relevant to this section. And then last problem. So find the partial fraction decomposition of each rational expression. So in this case, we have a new one. So here, x minus 1 is linear, but it's repeated. So we have to have a repeated term for it, basically. And this one is an irreducible quadratic. If you wanted to check the determinant, you could, or you can just show that like x squared plus 2 equals 0 means x squared equals negative 2, which means x equals plus or minus 2i, which is not real. Okay, so this is irreducible quadratic like we had before. This is linear repeated. So for this case, we write the original. We write a over x minus 1, but because it's repeated, we need another one. So we have b over x minus 1 quantity squared. And we do that because it could be made of just this to the 1 or to the second. We don't know which one, so we have to have one term for each. Here, since it's an irreducible quadratic and not a repeated linear, we have to have a linear term on top, the cx plus d. So once we have that, we can multiply everything by the denominator. So when you multiply the original, the whole denominator cancels. When you multiply by the a term, just one of the x minus 1 term cancels. When you multiply by the b term, the x minus 1 squared cancels. When we multiply by the cx plus d term, the x squared plus 2 cancels. So as you can see, this definitely took a lot of work. But here I am just distributing the variables. And once I still distributing in this step, it took a second, but you're free to pause and look at my work. Here I split them up, so I put the x cubes together, I put the x squareds together, I put the x's together, and I put the constants together. And then I factored out the x cubed, the x squared, the x, and the constant, which means now we are left with several equations. So here we have where's my first equation? Oh, here's the original. So a plus c equals 0 because the coefficient of the x cubed term is 0. Negative a plus b minus 2c plus d equals 10. 2a plus c minus 2d equals 2. And negative 2a plus 2b plus d equals 0 because there is no constant on the left side. So here my first step was to say that a equals negative c. And then here I've replaced every a with negative c. So now I have 3 equations, 3 unknowns. And then I came down here and rewrote them nicely. And then using this equation right here, I solved for c. And then I plugged this c value in everywhere there was a c in the other 2 equations, which were these ones. And now we have 2 equations, 2 unknowns. So here I use the elimination method to get 3b equals 12, b equals 4. And if we know b, then we can find d by plugging it in. So d equals 4/3, which means now we can solve for c by plugging in d. So c equals negative 14/3, and a was negative c, so a is just a negative. And now once again, that is not the final answer. The final answer is when you plug in the a, b, c, and d into the problem, which means this original is exactly equivalent to 14/3 over x minus 1 plus 4 over x minus 1 squared plus negative 14/3 x plus 4/3 over x squared plus 2. Okay, that is all I have for you. Have a wonderful day.